Hello and welcome to the second video on the molecules and matter topic, and this one's on changes of state and specific latent heat. So first thing, fly through this really, it's quite straightforward. You've got the 6 changes of state, 4 are very simple and you'll probably remember, although the diagram isn't that easy with that word there, but we'll make a start. Solids, when you heat up a solid, eventually it will turn into a liquid, and that change of state is known as melting. Think about water, ice melts into liquid water. If you continue to heat up the water, the liquid water, it will become a gas. Now here we've got the word vaporization, which is important because we do need to know about vaporization later, but you will know that word as boiling. Not evaporating. Evaporating is slightly different, although it does involve liquids turning into gases. So what we just need to remember is when you heat up a liquid and it reaches its boiling point, it will boil and not evaporate. Going back down the other way, you start off with a gas, you cool it down and it condenses into liquid. Condensation is the state change. Continue to cool your liquid down and it turns into a solid, and that's freezing. 2 other ones you may not have heard of, because it is possible for solids to turn straight into gases if the chemical is right. Iodine tends to do this. If you heat up from a solid to a gas, you get sublimation. So the solid will sublime into a gas. And then the opposite of when a gas turns into a solid, you get deposition. Okay, bit more complicated this, the heating curve. So all this graph is there to show is what would happen if you started off with a solid. In this case it looks like it's water. If you started off with ice at minus 40 degrees and you heated it up and plotted the temperature on a graph, this is what you would get. So first thing just to keep in mind, that when you heat up matter, when you heat up things, the particles gain kinetic energy. In other words, they move more. So imagine a solid with the particles held in position. If you start to heat it up, those particles will start to vibrate more and more. The hotter they get, the more energy they absorb, the more those particles will be moving, and the higher the temperature. In order to change the state of the matter, you actually need to break those forces. So think back to the first video, we said the solids have very, very strong forces holding the particles together. Liquids have weaker forces, and what's happened is when the solid has become a liquid, those forces have been overcome, they've been broken. And then obviously here with a gas there's no forces, so when you boil the liquid you overcome those forces, you break those forces. So if we just start with this, the graph, if we're down at minus 40 degrees, so imagine solid ice, those particles very vibrating very less, not very much, very little vibration in those particles. You stick it in a beaker and you put it over a Bunsen burner and you start to heat it up. What will happen is those particles will start to vibrate more and more. As you supply them with thermal energy, the particles gain more kinetic energy. They move more. And as a result, the temperature starts to rise. So water at minus 40, the particles will move less than if the same water at minus 20. So minus 40, not very much movement. Minus 20, more movement, and so on. When you get to this point though, this is not really what you'd expect. You'd think that if you were heating up ice and into water, the temperature would just continue to rise, but it doesn't. You get to a point where the graph levels off. In other words, I'm still heating up the water, I'm still supplying it with energy, but the temperature is no longer rising, and that is what happens when the ice melts. What's happening here is the energy is not being used to make the particles vibrate more. It's being used to break those forces between the particles. So here, point A, this diagonal line, the energy that you're using, supplying, the thermal energy, is being used to make the particles vibrate more. Here, the energy is being used to break the forces. Once all the forces have been broken and all that water is now liquid, the temperature starts to rise again. So once again, the energy you supply the ice with, or the water with, is being used to make those particles move more. So now in a liquid, remember, the particles can move. They don't just need to vibrate. So you supply the liquid with energy, the particles get more energy, they move faster, and the temperature rises. And again, the same thing will eventually happen. The water will start to boil. And again, you can see that the temperature isn't rising, even though I'm supplying it with heat. What's that heat energy being used to do? The same thing as here. The energy is being used to break those forces. Once all those forces have been broken, the water can again, temperature can rise. So two things to really be to try and remember. When the temperature's rising, it's because the thermal energy is making the particles move more. When the temperature isn't rising, the thermal energy is being used to break those forces. So this statement here talks about the diagonal lines. This statement here talks about the horizontal lines. Just a quick aside, temperature is basically a measurement of the kinetic energy of the particles. So if the water has a higher temperature, the particles will have more kinetic energy. They will move about more. And the last thing to keep in mind is that the total kinetic energy, the movement of the particles, and the potential energy in the particles is known as the internal energy. So if we talk about internal energy, we're essentially just talking about how much energy is inside or stored in those particles. The last thing we talk about, or need to talk about, is this thing called specific latent heat. Not quite in there. I'll leave that there. So, specific latent heat. Melting or boiling basically requires energy. As we've just said, you need that energy to break the forces between the particles. And that energy that's used is called the specific latent heat. Why is it latent? Well, latent means hidden. And if we go back to this graph, you are still heating up the particles here, but because the temperature is no longer rising, it looks as though that heat energy, the effect of that heat energy, is hidden from view. You can't see the thermometer rising, the temperature's not rising. So that's where the word latent comes from. So specific latent heat is basically the amount of energy needed to melt, or boil, that should say, 1 kilogram of a material. There's two different ones. You've got the specific latent heat of fusion, which is the fancy way of saying the amount of energy needed to melt something, and you've got the specific latent heat of vaporization. Going back to that first diagram, remember vaporization means boiling. So the specific latent heat of fusion tells you how much energy is needed to melt something. The specific latent heat of vaporization tells you how much energy is needed to boil something. And there you've got the formula and the formula triangle. Remember, those two types, fusion and vaporization, will be different. So you can see, generally speaking, it requires less energy to melt something than it does to boil something.